Okay, so today we're going to do some things with linear and exponential functions. We are going to compare linear and exponential functions. So by the end of this lesson, you will be able to compare and contrast the differences between the two types of functions, their graphs, their slopes, their average rates of change, things like that. So first, in these two examples that we're going to do, it says fill out the following tables. What patterns do you observe forming? So I'm given a table of x values. I need to plug in each of these x values. So first we have 0. So I'm going to plug 0 in for everywhere I see an x. So 0 and 0. So I now have f of 0 equals 3 times 0 plus 2. I come out with a 2. So when I plug in 0, out comes a 2. Remember, saying f of x, that's our function notation. It's the same thing as y equals. So then I continue this pattern. Then I plug in a 1. So then I get f of 1 equals 3 times 1 plus 2. And I end up with 5. I plug in 2. f of 2 equals 3 times 2 plus 2. I end up with an 8. I have to plug in 3. So f of 3 equals 3 times 3 plus 2. I end up with an 11. f of 4 equals 3 times 4 plus 2. I end up with 14. So what are some things we notice about this table? Well, first, let's look at what our y values or our f of x values are changing by. 2 to 5, that's plus 3. 5 to 8, plus 3. 8 to 11, plus 3. 11 to 14, plus 3. So we have a constant rate of change in our y values. And if we look in our x values, we have a constant rate of change. In our x values, we are adding 1 every single time. All right. So what I also notice is if we take a look at the formula, there's the slope and our y-intercept. So those are some things that we can identify with the information we already know. So we're going to do the same thing over here for g of x equals 3 to the x times 2. So I'm going to start with 0. I need to plug in. So g of 0 equals 3 to the 0 power times 2. So 3 to the 0 just simplifies to a 1. So 1 times 2, I should get a 2. And I did. All right, so now I'm going to plug in 1. When I plug in 1, I plug in 1 for x. 3 to the first power is 3 times 2. I get 6. Now I'm going to do 2. So I need to plug in 2. If I plug in 2, I get 3 squared times 2. I end up with 18. I plug in 3, I get 3 to the third times 2, and I end up with 54. Then I do 3 to the fourth power times 2, and I end up with 162. So let's look for a pattern. What do we notice? Well, let's do the same thing here. Is it increasing on both sides at a constant rate? 2 to 6, well, that goes up by 4. 6 to 18, that's definitely not 4. Then we jump even higher, 18 to 54. Oh man, these are definitely not changing at the same rate. So we can roll out that it's linear. But if we look at this, 2 times what is 6? 2 times 3 is 6. 6 times 3 gives me 18. 18 times 3 gives me 54. 54 times 3 gives me 162. This is what we call, right here, a common multiplier. When we have common multipliers, that means we have what we call sorry about that. We have exponential function. Oops. An exponential function. The first one we had was a linear function. So some of the differences: a linear function has this constant rate of change, an exponential function has a constant multiplier. All right, on to our next example. Example 1. We're going to determine whether each table represents a linear function or an exponential function, and explain your reasoning. So looking at this one, what we find is that we need to look for something. We need to look for a pattern. We have two patterns that we just distinguished, either a constant rate of change or a constant multiplier. So I want to remind you, if a table has a constant multiplier, it's an exponential function. So let's look at the x values. 1, 2, 3, 4. Well, we're obviously going up by ones. Let's look at our y values. 2, 8, 32, 128. So if I take a look at these, I'm going up by 6, up by 24, then up by 96. So it's definitely nonlinear. But now we need to figure out, is this an exponential function? We look here. 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. This is our constant multiplier. We have an exponential function here. Okay, so another example. We need to classify this, linear or exponential. So I'm going to look for a constant rate of change. My x values I know are constant. They're changing by ones. Now I'm looking at my y values. 6 to 9, 9 to 12, 12 to 15. I have a constant rate of change of increasing by 3 every time. So I have a constant change in the x and a constant change in the y. This gives me my slope. All linear equations have slope. We have a linear table. Okay, so example 2. Now we want to know, can you model the situation by using a linear function or an exponential function? So we're classifying. Then we need to explain our answer. It says Jack pays $30 each month for a gym membership. Well, let's think about this. So every month he takes $30 out of his wallet and he pays. The amount he pays per month is not increasing. It is always $30. So we have it that it's constantly changing $30 each month. This is a linear function. What if Jack's membership fee tripled every month? Those are one of those buzzwords, I would say. Tripled means it's being multiplied by itself 3 times, right? So if we look at this, that means each month he's not paying $30. Each month the amount he's paying is increasing to a different rate. So tripling means we have a constant multiplier. This would be modeled best by an exponential function. Now we have the initial bacteria population doubles every 5 hours. Buzzword. So again, we have an exponential function because we have a constant multiplier. Then it says Caitlin can buy shirts for $15 each. That is constant. It is not changing or multiplying by anything. That is best represented by a linear function. All right. So now we are on to calculating what we used to know as slope for linear functions. Now instead of slope, what we talk about is called an average rate of change. Because if we think about it, the graph, so we have to remember that the graph of a linear or of an exponential function, looks something like this. We have the x and y axis. Let me find a different color here. Let's do green. It starts here and we get this nice curve. Wow. All right. Not the greatest at this, I'm sorry. There we go. So we get this nice curve. This is an increasing linear function. But as you can see, the rate of change is not constant. With a constant rate of change, we have a linear function and we get a nice line that looks like this right here. This would be a linear. So you can see the difference in the constant rates of change. One has a constant rate of change, one has an average rate of change, depending on what part of the graph you're looking at. So the average rate of change of a function f of x over an interval a is less than or equal to x, which is less than or equal to b. So this is just saying from the number a to the number b. It's going to be in between those two numbers that we're looking at. We find this average rate of change using this formula. This is an important formula. Please highlight, put a star next to it. Anything you need to do to remember this formula, okay? Rewrite it 10 times, practice using it on the homework, do the examples on your own, something. But this reads, the average rate of change is equal to f of b minus f of a all over b minus a. So f of b is the value of the function at b. F of a is the value of the function when you plug in a. And then we have the number b minus a. So a and b, we're going to plug numbers in for these. So I know this is a harder concept, but think about it. How do the average rates of change for a linear function differ from the average rates of change for an exponential function? That's like what we talked about down here, looking at this graph that I roughly sketched. Okay, so think about it, a linear function. What do we say about the rate of change of a linear function? Well, it's always constant. The rate of change for a linear function is constant. That differs from an exponential function. How? Well, the rate of change for an exponential function is not constant. It changes over time. It's different. Those are the key concepts. But now we're going to take this formula that I highlighted in yellow and we're going to try to apply it. So if we take this and apply this formula, let's see how it works. All right, so it says graph each function over the domain. Remember, domain is our x. Oops, let's use a different color so you could see it better. Remember, domain is our x values, okay? Domain is x. That's why over here in this we have 0 is less than or equal to x, which is less than or equal to 6. So remember, on the last slide, this was your A, this was your B, okay? It says find the average rate of change. So this is like finding slope, but with something that doesn't create a straight line, I should say, for each function over 3 different intervals. So we have 3 intervals that we have to pay attention to. Here's the first, from 0 to 2. Second is 2 to 4. And the third is from 4 to 6. So down here, I have outlined those. I'll highlight them for you. And I'm going to do that work right underneath these so everything stays organized. So it wants us to describe what we observe. First, before we even get started, I'm going to create a table and I'm going to graph this because I think having a visual is going to be really helpful here. So I'm going to choose for this one, because it says over the domain 0 to 6, I'm going to choose 0, 2, 4, and 6. I get these numbers, okay? I get these numbers from these intervals that I am highlighting, so 0, 2, 4s, and 6s. So I'm going to use all those because that's what this problem is focusing on. And I don't want to create more work for myself. So I plug in 0 into this function, and I get 2 times 3 to the 0 power. Well, 3 to the 0 power is 1, so 1 times 2, I get 2. And then I keep going. I plug in 2. So 2 times 3 squared, well, 3 squared is 9. Then I have 9 times 2, that gives me my 18. So I'm creating a table here. And these are going to create ordered pairs for me to go graph it. So I finished my table by plugging in 4 for x, and I get 3 to the 4th times 2, that's 162. Then I get, I plug in 6 for x, so I get 3 to the 6th times 2, I get 1,458. So if you come to the right, I graphed these points on my graph. I have each point here, and you get to see what we're talking about. Because now we're computing the average rate of change over these intervals. So the first one we did in yellow from 0 to 2. So 0 is right here, 2 is right here. So we're finding the average rate of change between these two yellow marks. Then we're going to go find the average rate of change between 2. So I'm going to mark 2 and 4. So then I'm finding the average rate of change between the two green marks. And then in blue, I have from 4 to 6. So I'm going to mark those here. So between 4 and 6, the blue marks, then I'll find the average rate of change between those two. So I know it looks really confusing, but I promise it's not. We're going to use our formula, which I have written here, and I plugged in my values. So to remind myself, I put an A above the left number and a B above the far right number, and I'm plugging directly into this formula. So I have f of 2 minus f of a, or f of 0, excuse me, all over 2 minus 0. So to find out what f of 2 is, I come back over to our table with my highlighter, and I look over here. When I plug in 2, that's what f of 2 stands for, out pops an 18. All right, let me change that so you can see it better. So let's do yellow. All right, so f of 2, out pops an 18. So I plugged in an 18 there. Then it says minus f of 0. That means I'm plugging in 0 and I'm seeing what that number is. F of 0 is 2. So then I have 18 minus 2. And then at the bottom, I use the numbers given. So 2 minus 0, that gives me 2. So I simplify down as much as I can. I get 16 divided by 2 equals 8. So my average rate of change from 0 to 2 is 8. That is my average rate of change for this interval. All right, now I'm doing this for the interval 2 to 4. So I'm going to follow the same exact process. So I have my formula, and I'm plugging directly in. So I get f of 4 minus f of 2 all over 4 minus 2. So again, to find what f of 4 equals, I go to where 4 is plugged in. When you plug in a 4, out comes a 162. So I'm going to replace f of 4 with 162. So that's right here, as you can see. Then I have to find f of 2. Well, we found that earlier. F of 2 is 18. So I get 162 minus 18. Then on the bottom, I have 4 minus 2, which is your B minus your A value, which gives you another 2. So it's 144 divided by 2. That simplifies to 72. So my average rate of change on this interval is 72. Okay, so I'm labeling it on the graph so you see what we're talking about. Then I have my very last interval, so from 4 to 6 marked on the graph in blue. I'm going to plug into that formula again. I have f of 6. So I got to go figure out what f of 6 is. So I go over here, f of 6, out pops a 1,458, so I plug that into the formula, minus f of 4. If I look at f of 4, that's right here, out pops a 162. So on top I have 1,458 minus 162. And then in the bottom of the fraction, I have my b minus a, which is 6 minus 4, which still I have a 2 on the bottom. And then I look at this and I simplify and I get a 648 is my average rate of change on my blue interval, which is from 4 to 6. All right. So as a reminder, this is like finding slope for a graph that does not create a straight line. So this is essentially our slope formula for nonlinear graphs, but we call this finding the average rate of change, whereas in linear equations, it is the constant rate of change. All right. So from here, what I would like to talk about is our next example where we're applying this very same formula. So now we have another function. We're going to apply the formula, but before we do that, we're going to create a table of values, which I have created already. We're using the same intervals as the last example, which you can see on your notes packet. So I have them here again, and I will highlight them so you can see them. We have from 0 to 2, from 2 to 4, and from 4 to 6 are the intervals. Remember, so as a reminder, the value on the far left is your A in the formula. The value on your right is your B in the average rate of change formula, okay? So then I go about my business and I graph this. Well, I'm finding that the graph is linear. So when I'm computing this average rate of change on these intervals, I should find that they're all the same, because with a constant rate of change, it should be a constant change that I'm finding. So I'm going to highlight the intervals from 0 to 2, then we're going from 2 to 4, so I'm highlighting right on the graph, and then we're going from 4 to 6. Ooh, that one's big. All right, so we use our formula from our notes, which is f of b minus f of a all over b minus a. So I'm plugging in my values for the yellow interval, f of 2 minus f of 0 divided by 2 minus 0. Well, we look over at our table of values, which is very helpful in this case. F of 2, I get a 9, so I plug in a 9 there. F of 0, I get a 1, so I plug in a 1. So on top, I have 9 minus 1 all over 2. All right, that gives me 8 over 2, which simplifies to 4 right here. So I'm going to go over to my interval and type in a 4 just so we can see. So the average rate of change from 0 to 2 is 4. All right, well, let's keep going. We're going to keep using our formula. All right, f of 4, remember that's our f of b value, minus f of 2, which is our a value, all over b, which is 4 again, minus 2, which is a. So I look to my table. My table is what's really helping me here. F of 4 out pops a 17, so I plug in a 17. F of 2 out pops a 9, so I plug in 9. So 17 minus 9 gives me 8. Then I look at my denominator. 4 minus 2 is 2. 8 divided by 2 is 4. This is awesome. It's working out perfect. We have a linear equation. And if we think about this, we should be getting the same rate of change over each interval because this is graphing a straight line. So far, so good. Let's try our last one. Remember, 4 is our A value, 6 is our B value, so f of 6 minus f of 4 all over 6 minus 4. So I look to my table yet again. F of 6 out pops a 25, so the value is 25. F of 4 right here out pops a 17. So 25 minus 17. Then I look to my denominator. 6 minus 4 is 2. So I get an 8 over 2 yet again, which gives me an average rate of change of 4. So that means we did it right. If you look at our graph, we should get the same average rate of change because it's linear. And if we look at our equation up here, we have a slope of 4, so this makes sense. It makes sense that we would get the same exact average rate of change for every single interval. All right, so that's all for this lesson. If you have questions, make sure you ask them. Use your notes on the homework. Rewrite the formula multiple times. It will help you, I promise. So remember, the average rate of change formula is f of b minus f of a all over b minus a. It is now at the bottom of the page for you. This is the formula we've been using. This is very important. So when looking at this, it's important to rewrite it. And so remember, we can compare linear and exponential functions. Linear functions have a constant rate of change, while exponential functions have a rate of change, but it is not constant. And we calculate that by using our rate of change formula provided in this lesson. Additionally, if we're looking at a table of values, we find out whether that table is linear or exponential by looking for a constant rate of change or a constant multiplier. And that wraps us up for lesson 5.2 on comparing linear and exponential functions.